Let us now see a demonstration on a very important instrument which is used, what is called optical time domain reflectometer or OTDR. The OTDR is used to monitor the condition of optical fiber even after it is commissioned in the system. So, you see it is a very compact device in which the light is launched and the scattered light is received, and that is displayed as a function of time or as a function of distance. So, OTDR essentially receives the reflected light from different locations on optical fiber, and by that it tells you the status of the optical fiber. So, this is the display which you see. It can work in different modes. These are some advanced OTDR features. You can choose any of these three for operations. So, let us go to the basic OTDR mode. This is the start button, and after fiber is connected, you can start. That is the typical display which you see on the OTDR screen. So, the here horizontal axis gives you a distance and the vertical axis is in terms of dBs. These are the different locations. What is the status? That is what actually is displayed here. So, it shows you location. You can also see the events which are different locations. What is the condition of the fiber? This is for recording the data. You can have different settings. You can put distance in meters or kilometers. You can decide the pulse length. You can choose the wavelength at which you are calculating the condition. So, either 1310 nanometer or 1550 nanometers. These are various parameters which the OTDR uses for estimating the condition of the optical fiber. These are the source settings. Again, as we mentioned, two wavelengths can be used. That is the modulation rate, the pulse rate which is used for sending pulses. Let us now conduct the experiment by using OTDR. So, we have this fiber spool here and we want to find out the loss parameters of this optical fiber. So, you see this is a connectorized fiber and this connectorized fiber can be connected to OTDR from this jacket. So, now the fiber is connected to OTDR. And now we can start the OTDR mode. We can choose any of the two wavelengths. So, let us say we choose 1310 nanometer wavelength. And we can start the start button. And this shows that now the light source is on. So, the optical pulses are launched inside the optical fiber and the reflected light is integrated and measured. As you know, since the scattering of light is very weak inside the optical fiber, one has to integrate the reflected signal to improve the signal to noise ratio. So, before the things are displayed, many pulses are transmitted inside the optical fiber. The data is collected now and it is displayed. So, you see this is the trace of the OTDR. So, as we saw, the x axis is the distance and y axis is in terms of dBs, which measures the loss. So, one can see here the length of the fiber is about 4.4 kilometer, that is what is shown here. So, you see you are having the scattered light reduces continuously and difference between this and this essentially tells you the loss inside the optical fiber. And at this end there is an abrupt cut off because the fiber is ended. So, beyond this there is no trace of the scattered light. So, you see the sloping line here tells you the loss on the optical fiber. So, the data shows here is that you are having one reflection which is minus 47.6. Another reflection is from my other end of the optical fiber which is minus 49.7. The distance of the fiber is 4.4 kilometers and the total loss on the fiber is 1.422 dB. So these are the parameters which are used. The pulse width is 30 nanoseconds. The time taken is 45 seconds. The span length or the length of the fiber is 4.4 kilometers, and the total loss on the optical fiber is 1.42 dB. So that gives you the attenuation constant on the optical fiber. It is 0.322 dB per kilometer. Let us now conduct another experiment. This is another fiber. The fiber is connected to OTDR. We go through the same process. Go to OTDR mode. Let us do the experiment now on 1550 nanometer. Laser is on now. Data is acquired. You see the time remaining here. Okay, the data has been acquired and now it is displayed on the screen. So you see something interesting here. You are seeing a sharp peak at this location. There is another peak at this location, and then the signal drops rapidly. This is the enlarged version of the trace. So you can see from here to here, this is the fiber. The loss is not really very large, but then you are having these two peaks here, which are what are called the Fresnel reflections from the two ends of the optical fiber, one the near end, one from the farther end, and beyond this there is no optical fiber, or it's a very lossy medium here. So slowly the light intensity dies down. So this is a 1 kilometer long spool of optical fiber We can again see the analysis. These are the reflections which you are seeing from different locations. And that is the loss you see here, 0.343 dB, which is over a distance of this 1 kilometer. Actually, we have here another fiber which is a very bad quality fiber which is connected. So, this is a good fiber from here to here. This is the joint, and there is another very bad quality fiber which goes almost up to this point, which is 2 kilometers. So, you see here the loss is not much, but on this fiber which is not a good quality fiber, in bad state. So, you have a significant loss on this 1 kilometer. And again you see here a Fresnel reflection which is from other end of the optical fiber. Now what we can do is, we can take these two spools of optical fiber and connect it, and we would like to see from OTDR the signature of these two fibers plus also the location of the joint. Okay. Distance we have to increase now, because there was one spool of fiber which was 4 kilometers, the other one was 2 kilometers. You can set the pulse width, which essentially decides the resolution of the faults on optical fiber. That shows the acquisition time. You have chosen the time to be 60 seconds. You have pressed the start button now, and data acquisition starts. So you see, initially you see a lot of noise, and after more and more data is acquired, because of integration the signal to noise ratio improves and the noise goes down. Fourteen seconds left. The acquisition is complete now, and we get final display. We see here now, this is the fiber, which is the first fiber which we had tested. There is a second fiber which we had tested, and at the joint you have a substantial loss So, you see suddenly the power drops at this location, and then this is the fiber, this is the loss in the second fiber. These peaks which you see here, this peak, these are the ones which come because of the Fresnel reflection. So, that is the 4.4 kilometer length of the fiber. So, you can see here because of the connector, the loss is significant here. So, it is not a good connector. So, these are the parameters for the first fiber, 4.4 kilometer distance, 1.4 dB loss.
In this experiment, we will do time domain measurement of material and intermodal dispersion. This is the experimental setup. We will be using two fiber reels. This is a 2-channel CRO. This is a waveform modulator. This is a laser transmitter and photoreceiver. This is a waveform generator. This is a LED transmitter and laser transmitter. And we have a photoreceiver. The photoreceiver takes the optical input and give the signal output to the CRO. The output of the waveform generator the RF input of the laser transmitter and optical output. The output of the waveform generator is fed to the RF input. The output of the waveform generator is fed to the input of laser transmitter, and the optical output of laser transmitter is fed to the photoreceiver. The received RF signal is then seen on a CRO. Channel 2 is the received signal. Channel 1 of CRO is connected to the output of waveform generator. Here you can see the channel 1, that is the waveform generator on the CRO. This is the output of the waveform generator on channel 1. The frequency of the waveform can be adjusted. Channel 2 shows the waveform of the received signal after passing through the small patch of fiber. Here we will first estimate the rise time of a laser transmitter. You can clearly see the rise time of the received signal is higher. You can see that the rise time of the received signal after transmitting it fiber is higher. As we decrease the amplitude of the laser, the amplitude of the received signal also decreases. We will now measure the rise time for laser. Cursor 1 is at the 10% level, which shows minus 10 nanoseconds. Now we will adjust cursor 2 to 90%. Cursor 2 is at 3 nanoseconds. Now switch off the laser transmitter. Now we will connect waveform generator, LED transmitter and photoreceiver. The output of LED transmitter is connected to the photoreceiver. And output of waveform generator is given as RF input to the LED transmitter. The output of photoreceiver is seen on channel 2 of the CRO. The channel 1, the channel 2. Channel 2 is the RF output of the photoreceiver. Here also, now we measure the rise time of LED. We adjust the cursor 1 to 10% of the maximum amplitude. Cursor 1 is at minus 6.8 nanoseconds. Now we adjust cursor 2 to 90% of the maximum amplitude. Cursor 2 is at 8.8 nanoseconds. We will now connect graded index multimode fiber between the transmitter and receiver. These are the fiber specifications. We are connecting two spools. Via this connector. ST to ST type of connector is used to connect the two spools. We have now measured the rise time of LED and laser. Now we will connect the fiber between the transmitter and the receiver, and we will see the difference in the rise time because of dispersion. Then we will subtract the effect of the rise time of the source, that is LED and laser, and we will get the rise time because of dispersion. The output of the LED is connected to the fibers. And the other end of the fiber is connected to the photoreceiver. So now light will travel 3300 meter from the transmitter to the receiver. Again we see the RF output on the CRO. Here we can see the rise time of the received signal is much higher than that of the transmitted. Channel 1 is the output of waveform generator. We will now measure the rise time of LED transmitter. Again we adjust the cursor 1 to 10% of the maximum. Which is minus 15 nanoseconds. Cursor 1 is at minus 15 nanoseconds. Cursor 2 is at 12 nanoseconds. Difference between the reading of cursor 2 and cursor 1 will give us the rise time. Now we will connect the two spools of fiber between the laser transmitter and the photoreceiver. The output of laser transmitter is connected to the fiber and the other end of the fiber is connected to photoreceiver. The RF output is seen on channel 2 of the CRO. So as we increase the power of laser transmitter, after a certain value, lasing starts and we get a sharp increase. Below the lasing current, received signal was very less. Here also we can see an increase in the rise time. We will now measure the rise time of the received signal. We have now adjusted cursor 1 to 10% of the amplitude. Similarly, we will adjust cursor 2 to 90% of the amplitude. Cursor 2 is at 9 nanoseconds. And cursor 1 is at minus 10 nanoseconds. difference between these two readings will give us the rise time of the laser plus the reel 1 and 2. We will now measure the dispersion in the fiber. For that, we will first calculate the fiber rise time for laser source and LED sources. The rise time for laser plus receiver system is calculated as follows. From our readings, cursor 1 was at -10 nanoseconds and cursor 2 was at 3 nanoseconds. So the rise time of the laser plus receiver system comes out to be 13 nanoseconds. Similarly, the rise time of the laser plus fiber plus receiver system comes out to be 19 nanoseconds. Now this total 19 nanoseconds has the effect of the rise time for laser and receiver system as well. So to calculate the rise time of the only fiber for laser source, we subtract it from the total rise time. So we get the fiber rise time for laser source as 13.384 nanoseconds. Now similarly, we will calculate the fiber rise time for LED source. The rise time for LED plus receiver system from our readings comes out to be 15.6 nanoseconds, and the rise time of the LED plus fiber plus receiver system comes out to be 27 nanoseconds. So as in the previous case, we will subtract the effect of rise time of LED plus receiver system from the total rise time to get the fiber rise time for LED source, and the fiber rise time for LED source comes out to be 22.037 nanoseconds. Now we know that the spectral width of the laser source that we used is 1 nanometer, whereas the spectral width of LED source is 30 nanometers. Therefore, we can assume that the laser source experiences negligible material dispersion as compared to intermodal dispersion because of its narrow spectral width. So, pulse dispersion in fiber with laser source is assumed entirely due to intermodal dispersion, whereas dispersion in fiber with LED has contribution of material as well as intermodal dispersion. We will now use this information to calculate the intermodal dispersion and material dispersion in the fiber. From our previous argument, the pulse broadening due to intermodal dispersion is captured by the rise time of fiber for laser source. So we take the pulse broadening due to intermodal dispersion as the rise time of laser source, which is 13.384 nanoseconds. From this we calculate the intermodal dispersion as the pulse broadening due to intermodal dispersion tau Im divided by the length of the fiber, which is 3.374 kilometers. So we get intermodal dispersion as 3.97 nanoseconds per kilometer. Now to calculate the pulse broadening due to material dispersion, we subtract the effect of intermodal dispersion from the total fiber rise time for LED source, which is done in this equation. So we get the pulse broadening due to material dispersion as 17.5 nanoseconds. Now finally we calculate the material dispersion as dmat equal to the pulse broadening due to material dispersion tau mat divided by the spectral width of the source, which is 30 nanometers in this case, and the length of the fiber, which is 3.374 kilometers, and we get the material dispersion as 173 picoseconds per nanometer kilometer. Here we can see that material dispersion is negligible for sources of narrow spectral widths, whereas for sources whose spectral width is large, the material dispersion is comparable to the intermodal dispersion. In this experiment, we will measure chromatic dispersion with a WDM system and a ring resonator. Figure shows the schematic diagram of the experimental setup for demonstrating chromatic dispersion in wavelength division multiplexing system. We have a bit generator whose RF output is connected to the two lasers. The output of the laser sources is combined in the wavelength division multiplexer. The output from the one of the port is taken further. Now this bit generator generates pulses which modulates the output of this 1550 nanometer laser and 1310 nanometer laser. Because of chromatic dispersion, the pulses of different wavelengths travel at different velocities. So as they travel further and further, the separation between the two pulses increases. One of the method of achieving long fiber lengths in lab is to use a ring resonator. So here we have a WDM output which we give to a 50-50 coupler. So half of the power of port 1 goes to port 3 and other half goes to port 4. Now the power coupled to port 4 goes through 4 km long fiber and then again comes into the 50-50 coupler. Now again half of the power goes to port 3 and half of the power goes to port 4. So at port 3 we will get pulses. The first pulse will be coming directly from the input port 1. The second pulse will be coming from the port 2 after travelling 4 km length. Then the third pulse will be coming from the fiber which has travelled in this resonator twice. So it would have travelled 8 km and we will get pulses which have travelled larger lengths. The output of port 3 is collected by a photoreceiver and the RF output is seen on a CRO. So we will see the dispersion on the CRO. This is the experimental setup. These are the various components on the kit. This is the data generator which we are using. We set the output of bit generator to 0.01 megabits per second. We connect the output of data generator to 1550 and 1310 nanometer lasers. This is a 1550 nanometer laser. We have 1550 nanometer laser and 1310 nanometer laser. Both of which are fed with the output of bit generator. The output of 1550 nanometer is connected to the port 3 of WDM. And the output of 1310 laser is fed to port 4. This is a 1550 multiplexer. Multiplex signal comes out from port 1 and port 2. We use the signal of port 1. So the multiplex signal of port 1 is fed to the port 1 of 50-50 coupler. The port 2 of the 50-50 coupler is connected to 4 km fiber. The output is taken from port 3. And port 4 is connected to port 2 via 4 km long fiber. So it forms a ring resonator. The output of port 3 is taken to the photoreceiver. and you see the output in the CRO. Port 4 2 is connected to port 4 by 4 km long fiber reel. This is a 4 km long fiber of single mode. This is the photo receiver RF output. This is the output of the photo receiver. Channel 1, that is yellow line, is the transmitted data, and channel 2 is the received data. Here you can see that there are distinct peaks which correspond to the data rate which we had set. Now in channel 2, we can see that there are multiple peaks, each with diminishing amplitude. This is because after each pass of the signal in the 4 km fiber, we get some of the power at the receiver and some is again coupled to the fiber. So you can see the first peak on channel 2. It is a bit elongated as compared to that of channel 1. Now we will see the second peak at the receiver. This second peak at the receiver is after the light traveled 4 km in the fiber, after one lap in the fiber. This peak corresponds to the first pass in the ring resonator. Here we can clearly see that it is much more elongated as compared to the first peak. We will see the third peak. This third peak has travelled 8 kilometers in the fiber. Here we can clearly see the splitting of the pulse in two. Here we can clearly see the effect of chromatic dispersion, since the 15 nanometer signal and 13-10 nanometer signal travels at different velocities. So we get a splitting of the pulse. Now we'll see the fourth pass. This signal has travelled 12 kilometers in the fiber. Here we can see the original pulse is split clearly in two different pulses, one corresponding to 1550 nanometer, other corresponding to 1310 nanometer. As we see one further peaks, you can see they are separated even by a higher distance. You can see that they are separated with a increased time lag. You can clearly see that difference in the peaks